Okay, good morning in Switzerland and good evening in Japan. Welcome to the 14th EPFL CIS RIKEN AIP joint seminar. My name is Masashi Sugiyama. I'm director of RIKEN AIP. So I'm chairing the session today. So it's my great pleasure to introduce our speaker today. So Professor Lenka Zdeborova from EPFL CIS. So Lenka is a professor of physics and computer science in EPFL, where she leads the statistical physics of computation laboratory. She obtained her PhD in physics from University Paris-Sud and also from Charles University in Prague. And before joining EPFL, Lenka was a researcher at CNRS working in the Institute of Theoretical Physics. So today her talk is entitled Insights on Gradient-Based Algorithms in High-Dimensional Non-Convex Optimization. Okay, Lenka, so we are looking forward to your talk.
Thank you very much for having me here. So let me share the slides to show you some pictures and equations as usual. Thank you. So indeed, as said, I want to tell you something about what we try to understand about gradient-based algorithms in high-dimensional non-convex optimization. So as usual, I will start with basically motivation, that is, in a sense, understanding what's going on in machine learning, on deep learning in particular. So we kind of have one big good news and one big bad news in the learning theory, that at one hand, neural networks are universal approximators, but on the other hand, the optimization problem is NP-hard in the worst cases. And so that kind of raises the question, how comes that in practice it actually works, and where exactly theoretically does it come from? And these are not recent questions. I like to give this snapshot from an article that Leo Breiman wrote already 27 years ago, where he kind of pins down some of the questions about neural networks, such as why don't heavily parametrized neural networks overfit the data? What is the effective number of parameters? Why doesn't backpropagation have full pool minima? And these are pretty much the questions that we are kind of still discussing today. They are largely not answered in a satisfactory way. So, for instance, the one about the effective number of parameters, the way I like to think about it is to think about the sample complexity, the question of how many training samples are truly needed for a given task. So you can take your favorite algorithm and your favorite way of train and your favorite architecture and train on these benchmark tasks and get some performance, but we do not really know whether we can do better or not. And if we can do better, is it by changing the algorithm or changing the architecture or doing some combination of the two or something else? And similarly about the third question here, why doesn't backpropagation head for pool? And one can even erase the local minima, simply pool local minima that do not generalize really well. And that is also still kind of a mystery in the view of the empirical facts, that the neural networks that we are using are typically so over-parametrized that there are many global minima, really many, and some of them actually do generalize badly, and some of them generalize nicely. And for some reasons, the gradient descent algorithm manages to avoid the bad ones and go to the good ones with limited number of samples. So it's not because there are no bad minima, there are. The literature discusses some kind of implicit regularizations or learning simple functions first, but overall, I mean, the kind of satisfactory answer is not yet there. So that kind of leads me to a goal that one could set for oneself, which is to analyze generalization properties of gradient-based algorithms in settings that are non-convex, high-dimensional, and where the sample complexity is low as possible. So the non-convexity, the high dimensionality and low sample complexity, that's really kind of the key points here. And of course, if we could reach that goal in general, then we would solve a lot of these open questions about deep learning that's not yet the case. And in this talk, what I will walk you through is a setting where this can be done. So a simplified, I will say in which sense, setting where we can actually understand what's going on. So that setting comes from the idea of the teacher-student kind of setup for learning with neural networks, where we abstract away the kind of complexity of the task of the data, and we set the task the following way. So we generate the teacher, so we have generate data X, the input samples X, that will be IID random vectors. So not only sample from sample, they're IID, but also component from component, they're IID. So there's no structure in that input data. And then we set up a teacher network, for instance, the one drawn here, with weights that we choose at random. And that teacher network would generate the labels for us. And then the student network observes the inputs and the outputs as usual, and tries to learn from the inputs and outputs the right function. But it doesn't have, so it can be only simpler if we actually give the student also the architecture of the teacher, but crucially, it does not have the values of the weights. So of course, if it was somehow able to find the same values of weights, it would learn the same function, but even it can learn other weights to still learn a similar function. So that will be our question. Now, this teacher-student setting, it's not something that we came up with a few years back. That's actually a very kind of old idea to look at that setting as a kind of simplification of the overall task of learning in general systems with neural networks. The first paper that I know where it appeared is from 1989. It's in a work of physicists Elizabeth Gardner and Bernard Derrida, so the journal where it is published is a physics journal, where they look at this teacher-student setting in the simplest possible case, where both the teacher and the student don't even have hidden units. So it's just a single layer neural network, or generalized linear regression if you want. So I repeat again, the setting is that the input data are IID Gaussian. The weights that the teacher network is using, we will be calling them W star, are taken from some distribution, again, IID, but the distribution, we will be looking at different versions of this distribution. And then the teacher network creates the labels using some nonlinearity, for instance, a sign. That's what they use in this original paper, on the scalar product between the inputs and the weights. That's kind of the usual you would do in a single layer neural network. What is already interesting here is that already back then they looked at the high dimensional regime. That is when the dimensionality of the inputs D is going to infinity and the number of samples N is also going to infinity, but the ratio is some fixed number, say 5, imagine 5. Oh, sorry, this should be D here. So, what can they say about this setting? Well, here, I mean, the early results about the generalization error in this high dimensional setting actually came from physics, and there are textbooks written on that, maybe not all in the 90s, but certainly a long time ago. So as a first thing, what I want to do is to walk you through how the results coming or stemming from this line of work, from this literature typically look like, because it's a bit different. What one calls the result is perhaps different than from your, say, traditional optimization theory. So I walk you through that, and then we'll go through that setting, non-convex, high dimension, where we can understand something about gradient descent-based algorithms. So the first notion that I want to introduce is the base optimal prediction. So that is the prediction of labels on new samples, inputs X, that were not seen in the training set. And if in the setting of the teacher-student, where we really know the model from which the labels were generated, we can prove that there is no possibly better procedure than, or estimator than, the one stated here. That is, we write the posterior probability distribution of the weights given the input data and the labels, which is just given as a product of the likelihood of the labels given the weights and the inputs times the prior on the weights. That's the distribution that the teacher was using to generate its weights. And then the base optimal prediction of the new label, if we have a new input x new, is given by a posterior mean of the function that the teacher was using over this probability distribution PW. So that base optimal estimation is, of course, somewhat different from the usual empirical risk minimization, where we simply postulate some loss function and some regularization and minimize over the weights, then take the minimizer and evaluate on that minimizer. And of course, if we had really many samples and low dimension, there would the empirical risk minimization is optimal, so there would not be any advantage of the Bayesian optimal estimation. But in the limit that I'm discussing, where the number of samples is just a small constant more than the dimension and both are large, there is actually a constant improvement from the base optimal estimation over the empirical risk minimization. I will be showing you some graphs where these constants will become concrete. So the results in the form of the results in which came these results from the 90s, from the statistical physics literature, that is the following. So what is computed about the teacher-student setting is the so-called free energy, which is the high dimension limit of the expectation over the inputs and outputs of logarithm of the z, which was the normalization of the posterior. So at first, it's maybe not clear why that would be an interesting quantity, but in statistical physics, the free energy is then generating all other quantities of interest, which will be seen on the next slide. And the result is that this limit actually takes a very simple form, that there is a closed formula that depends on these two functions, phi p of w and phi p out, that are just integrals over maybe a pair or a triple of Gaussian variables or variables distributed from this distribution w. But the bottom line here is that we reduce the high dimensional computational problem, where dimension d was very large, to something that is just a function of two scalar variables. So it's closed form in the sense that this is considered the solution of the problem, in the sense that we have a very simple to evaluate formula that actually gives us the performance of the high dimensional problem in this limit. And the second part of the theorem is that once we have this free energy, it's very straightforward to actually derive from it quantities of interest, such as the optimal generalization error, which is we take the minimizer here and plug it into this expression, and that gives us the test error that no algorithm, no procedure can actually improve. So once we have this expression, we can plot it. And this is what is done here. In the case that we call the spherical perceptron, what is spherical or Gaussian there is actually the weights that the teacher is using. So the teacher uses weights that are just Gaussian numbers, zero mean unit variance, and then generates the labels using the sign, nonlinearity, and this scalar product. The inputs are Gaussian. And what is plotted here is the test error as a function of the number of samples over dimension. And the red line is evaluation of the formula that I gave you before. So you cannot get test error that is better than that. The blue points is a logistic regression. That's something that you would run, and any student would run and get in no time if they are skilled with machine learning. And the black points is the result of an algorithm that is called approximate message passing, AMP. And you're kind of seeing that the black points are on the red line. So let me tell you why is that and what is this algorithm, AMP. So approximate message passing algorithm is a message passing algorithm derived from what's called belief propagation, which is an approximate algorithm that you write the posterior and represent it as a graphical model. And then this is not a tree. Belief propagation would be exact if it was a tree. It is not, but you nevertheless write belief propagation. And then you consider that here actually every factor node and every variable nodes have many neighbors. And you can use that to actually simplify this belief propagation into a form that is called the approximate message passing, that has a pseudocode kind of sketched here. And it's very simple to represent. It basically only involves matrix multiplications with the matrix of the data and a vector of variables, which are the estimators of the mean of the weights and their variances. So it runs very fast, very simply. There are some special functions here that are involved. I mean, the details of it are not that important. There is a simple algorithm that actually follows from that. And not only it gives you the means and variances of the weights, but also it gives you the Bayes optimal prediction. It tells you what should be the label of a new sample given by the formula over here. So what is really interesting about this algorithm is that despite it being an iterative algorithm on a high dimensional space, so traditionally we would kind of not really know how to analyze step to step the error that it does. This one has, one can prove a theorem giving us a so-called state evolution of this algorithm, which tells us that the correlation between the ground truth weights and the estimator of the parameter is a parameter m that evolves in a very particular way using this, again, just low dimensional, just scalar evolution. Interestingly, of those functions that were the very same ones that appeared in the free energy that I showed you a few slides back. So it's very intrinsically, the behavior of this algorithm is very intrinsically related to the same formula for the free energy. And once this is put together, the corollary is that you have this one formula depending on two variables, scalar variables. And from the same formula, you can get at the same time the minimum mean square error of the learning, of the test error that is given by the global maximum of this function, or minimum, if depending what is the sign. And also the performance of this approximate message massing, its mean square error on the test error or on the estimation of the parameters that is given by the local maximum of that function that is reached starting from random initialization. But here it's just a basically scalar function. So analyzing where its global maximum and local maximum becomes very easy, even if it is non-convex. It's just the function one needs to plot. So that's this black points. That's the algorithm of that's the performance of the algorithm. And in this particular case of the spherical perceptron, the global and local maximum are the same. That's why these points exactly lie on the optimal curve. So in this case, the AMP is able to give you the optimal test error in the high dimension limit. Now you realize that this logistic regression, which is doing something quite different, is relatively close. This is just an experimental run. But you can also look at that into more detail. You can actually use the same methodology to analyze, to give a closed formula for the performance of the logistic regression in the same limit. And if you optimize over the regularization parameter, the usual lambda, then you actually in this plot get something that looks identical. But if you, in the sense that the test error reached by the logistic regression looks really close to the test error reached by the Bayes optimal estimation, but they actually are not identical. Since you have the formula in, as a function of one variable, you can evaluate it very precisely and see that there is a difference of the order of 10 to the minus 5, which in practice is probably completely irrelevant, but it's kind of not equal theoretically, but it's very close. So in practice, you'll be super happy to run logistic regression in this case, and you don't need anything more fancy in this particular case. So that's kind of a special case. So next we will go to another example of the teacher-student setting. So we will choose the activation function and the way the teacher generates the weights just a bit differently. It will lead to a non-convex problem this time, and it will behave quite differently. So the choice here is actually motivated by the problem of phase retrieval, which is a broadly studied problem in signal processing and imaging. Here we kind of simplified to set it in the teacher as a special case of the teacher-student setting. So what will not change is that the input data X will still be Gaussian IID, the teacher will still generate the weights as Gaussians. That's also the same as in the spherical perceptron. What is changing is that instead of generating labels that are sign of the scalar product, the teacher will generate labels that are absolute value of the scalar product. So I did not change much, just this. And then, okay, then the labels here are real valued. So then this is a regression problem. And we look at it as such. We look at the regression from the training data. So we want to be, again, able to generalize well, so predict the labels for new inputs. In phase retrieval, we rather go after reconstruction of this W star. So it depends whether we are looking at it as an inference problem or learning problem. Both are interesting and relevant. So we can apply the same formula because the same formula was actually written for any activation function phi. So we just need to change the sign for the absolute value and plot it again. And this is the plot. So the blue line this time is the orange, which is when you don't see orange, it's because it's hidden by the blue, is the optimal performance. So that's the best test error that you can get independently of the algorithmic procedure from this many samples. The blue line is the state evolution of the approximate message passing algorithm, and the red points are its run. So red and blue agree, but you see that there is a gap, that there is a small region here, or actually the approximate message passing does not reach the optimal performance. And that's called the hard region or hard phase. It's kind of interesting theoretically, because this approximate message passing is conjectured to be in some sense optimal among the efficient algorithms, those who run really fast, say linear in the system size. But at the same time, it's pretty small. You're just bothered if you have between the dimension and 13% more times the dimension samples. And if you have more, you're good. So it's very small. So maybe it's not such a big deal. But what kind of makes it so this is just a kind of physical interpretation of where this hard phase comes from. It's actually pretty much the same mechanism for which you can supercool water and keep it under 0 degrees Celsius still in the liquid state. That's maybe just a bit of a physics. But what is kind of more interesting is this suggestion of a mechanism that if the hard phase is there, even a very small one, then it causes hurdles for gradient-based algorithms for a large range of the sample complexities. And this is kind of a heuristically put forward hypothesis that we kind of put forward in this paper. But on the phase retrieval, one can actually look at this in more detail and more mathematically. So let's do that. So let's look at, again, the teacher generates the data as before in the phase retrieval way. But now we are not learning it in this phase optimal way. Now we are learning it using empirical risk minimization. That's something that one would do if one didn't know much about statistical physics and was to solve the problem. That would be one way to go about it. One would write a loss function. So say that you knew that the teacher is generating the labels as absolute value of the scalar product. You would want to adjust the loss function to that. Actually, if you didn't take here y square and the scalar product square, if you actually did not put the square, you would just take your usual square loss function, then you could do it, but you would see that you actually need number of samples that is quadratic, at least quadratic in the dimension. Whereas here we are talking some constant times linear. So that would not be a good way to do it. You could also actually try to learn it with something like a kernel method that also would need number of samples that is actually quadratic in the dimension. So one of my key points was to keep the sample complexity as low as possible. So this kind of excludes that class of learning ways, kernels and all related. We really need to go after something that is able to learn the features in a sense. And already this simple loss function without, there are no hidden units here, is just a particular case of a loss function, should be able to kind of find back the W star and get minimized there if there are enough samples. So and this, of course, the squares are making it a non-convex optimization problem. So that's kind of making it interesting. So let's see how it works in practice. Does it work in practice? So, okay, sorry, before that, just what do we know about that theoretically? So about minimizing this loss function for the data created this way. So there are several papers about that in the theoretical computer science literature. But okay, as I said, kernels would need number of samples that are quadratic in dimension. But gradient descent with this particular loss function was actually shown to need polynomial of logarithm of d times the d samples. So that's still much more than our 1.13, but okay, it's better than d squared. There is another paper that slightly changes the loss function that actually gets rid of these polynomial of log d factors. So that's kind of nice, but the constant there stays unspecific, so it can be very big. But nevertheless, okay, there is a constant complexity on the sample complexity under which gradient descent can learn this. But now, okay, let's just look how it is in practice if we just run it. In other words, is this proof tight, or is there a gap that it can be improved? So when we run gradient descent on the loss function a few slides ago, we go and fraction of success, where success here we call when the test error gets below some threshold, which was some small number in this case. So in what fraction of cases that we run, depending on the size. So here the n is actually the dimension, that's the dimensionality of the data. So how does that depend on that? And alpha here is the number of samples divided by dimension. So always the x-axis in all these plots is always the same. So we see that as the system is getting bigger, the performance is getting a bit worse. It's maybe shifting. These sizes are always a multiples of 2. So this could be a logarithmic shift to a larger alpha, or maybe saturate somewhere, but definitely say at alpha 6, it's not working for large enough systems. Okay. So if we put it back into this axis, maybe the numerics starts working something at 7, maybe it needs to grow as logarithm g. But what is clear from that little experiment is that there is a gap between what the gradient descent on that loss function is able to do and what we got from the approximate message passing that was giving us 1.13, and quite a sizable one. So is there some mechanism that can help us close that gap? What do we need to do with the gradient descent to close that gap? So this is somehow where, at least in my point of view, kind of this gets interesting, because there we go, okay, what's happening in deep learning? What do we need to put in to kind of make this a toy model of what we know is going on in deep learning? So, okay, before doing that, okay, maybe a recap. So in the spherical perceptron, when the teacher was generating the labels as signs, we had the empirical risk minimization that was so close to the base optimal that we wouldn't bother kind of wanting to improve the logistic regression here. In the phase retrieval is different. There is a sizable gap. So how do we close that gap, right? And in order to do that, as I said, let's kind of go thinking, what are we missing from what we usually see in deep learning that's not here? So deep learning is over-parametrized. So a hypothesis is, could over-parametrization here help the gradient descent? Let's see. So to analyze that, we need to write a loss function that actually uses a neural network with some hidden units, and we will use the simplest case where there is a single hidden layer of size m, and that all it does to the loss function is that just adds the sum over the hidden units here, and we rescale here by 1 over the size of the hidden layer. That's our new over-parametrized loss function. For the results that I'm going to show you to work, we actually need the number of hidden units here, m, to be bigger than the dimension. Not much, by 1 is enough, but we need it to be bigger. Okay, so then what does gradient descent do when it's minimizing this loss function, instead the one without hidden units where it was not doing really well? So that's something that we analyzed in this paper with my former PhD students, Stefano and colleague from New York, Eric van den Eyden. And we got about this specific setting the following theorem. So when the number of hidden units is larger than the dimension, if we call M of N and D the set of minimizer of the empirical risk, then we could prove that if alpha, that is still the number of samples over dimension, is between 0 and 2, then the set of minimizers does not includes more than just the kind of ground truth value A star. Here we call the A star is the teacher weights times its transpose. M star would be the number of hidden units in the teacher, but here we consider M star equal 1. And A is then the same thing for the student, but this time the student has many hidden units. So here we are showing that the set of minimizers, if alpha is small, is actually not just the right one. There are many other ones, and some of them would, there is no reason we would be actually finding the ground true A star one. On the other hand, when alpha is bigger than 2, then the set of minimizers with finite probability is only the ground truth A star. So what we managed to prove is this finite probability result, because that's of course often easier in these high dimensional settings. And we didn't kind of manage to prove that it's with probability 1, but as things always concentrate in these settings, it's very reasonable to think that this is just a weakness of the proof, that the actual result is that the probability that the minimizers is only the ground truth 1 is actually 1 whenever alpha is bigger than 2. And that is something that we can actually check numerically, that indeed the numerics is consistent with that. So this seems indeed as just a weakness of the proof. And we also put that together with the second theorem that is telling us that in this particular setting, the gradient descent actually does go to a minimizer. So if there is a unique minimizer, well, then it must go to that one. And if that unique minimizer has a 0 test error, which it does, the A star has a 0 test error, well, then it's enough to have twice many samples than dimension to get 0 test error. So if I put that back into my axis here, we got that without over-parametrization, we needed 7 or maybe logarithmically many. And okay, there are some, oh, sorry, the D should not be here. This is just a constant. But with the over-parametrization, just one hidden layer that is wide enough, but not infinitely wide, just wider than the dimension, just at least by 1. Then we get that the gradient descent actually needs only twice as many samples than the dimension. So it's still not as good as the approximate message passing, but it got significantly better. The over-parametrization helped the gradient descent to actually go to the right place, to actually not get lost in some of these non-convexities and find the right thing without losing the track of what the right function was, going to 0 test error. That's what the result is about. So there was kind of one interesting thing, that the over-parametrization is actually helping in this case to reduce significantly the sample complexity. What else do we have in deep learning that we didn't kind of play with yet in this setting? So far, we talked about gradient descent, but usually use stochastic gradient descent. So then there is the question of the advantage of the stochasticity, that, okay, in general, we have results for it, against it, it's not clear. Let's look at this particular setting. So of course, this is one setting, so that doesn't really imply anything strong in general, but it's an interesting case where we can study this in detail. So in order to study this in detail, what we thought back a few years ago, but okay, now we're actually writing a paper where we are not really needing that, but it still gives us kind of this variant of the stochastic gradient descent gives us something interesting. So let me introduce it. So back then we introduced this variant of stochastic gradient descent because we thought that it's the only one that we can analyze, that the stochastic gradient descent as it is, where it was not kind of, we didn't see how to analyze it back 2 years ago. So the trouble is that it seemed like if we want the flow limit of the stochastic gradient descent, then it is well known that for the vanilla stochastic gradient descent, the flow limit is just back the gradient descent. So it's in a sense not interesting, it's trivial. So we needed a version of a stochastic gradient descent where we would keep both the stochasticity and the flow limit to be non-trivial, in the sense different from the gradient descent. So in order to get that, we introduce what we call this persistent stochastic gradient descent. So all that changes is kind of the protocol with which you decide whether a given sample is part of your mini batch or not. In stochastic gradient descent, you just decide at random. Every time step, you go and pick a certain number of your samples, and that's your mini batch. In the persistent stochastic gradient descent, every sample actually has a Poisson process related to it, and the Poisson process has a persistence time, tau, and then at every time, the Poisson process decides whether the sample is or not in the mini batch. So that's where the word persistent comes from. If the persistence time is large or somewhat not close to zero, then every sample stays in the mini batch for some time, and then it goes away, and then it comes back, and it stays also for some time. It persists there for some time. And this is a version of stochasticity, that changes a little bit, that we actually, of which the flow limit is non-trivial. Now it is different from the gradient descent, and we could analyze it in the sense that we wrote what's called the dynamical mean field theory. So that's again something stemming from this volume of statistical physics literature. It's slightly different from the results that I have shown before. This one is really looking at the dynamics of gradient-based algorithms, but it can be done. The same thing can be done in the sense that from dynamics that is high dimensional, non-convex for the dynamical mean field theory, it doesn't matter whether it's convex or not. It doesn't require the convexity in any sense. The key thing is that it's able to describe this high dimensional system that a priori leads to high dimensional probability distributions, reduce it down to a scalar dynamical system. The cost of that scalar dynamical systems becomes non-Markovian, even though the original dynamics was Markovian. And there is a stochastic differential equation that actually drives the dynamics of this scalar stochastic system, where this h variable would be the variable of that system. So explaining the details of that, there's a very nice lecture of Pier Francesco Urbani a few years back at Les Houches, so I won't be kind of going into the details. That's a bit of a hurdle. I actually didn't add it here, but recently this mapping from the high dimensional system to the low dimensional system was actually proven by Andrea Montanari and collaborators. So as the other methods that at first were heuristic physics methods, now this is a theorem. So there is this effective scalar system that actually describes the dynamics, from which we can derive the test error at a given time and any kind of related quantity that we want. This is just the full set of equations to kind of state that system. I won't be going really into the details of that. But what do we get from it? So here is a plot of on the x-axis, we have average magnetization, which is the correlation between the ways that the gradient descent is currently having and the ground truth weights. So the bigger the better, because if we correlate with the ground truth weights, then we learn the same function. And there are three lines there. The blue and orange is gradient descent and stochastic gradient descent. The learning rate here is pretty small, so that's why the stochastic gradient descent is really close to the gradient descent, as it should. But the green curve, which is the persistent stochastic gradient descent, is actually doing something else. It's worse at first, but then it shoots up and gets actually a better performance at the times that are given here. So that's kind of interesting. And when we put it back to still the phase retrieval problem, the setting did not change, and look a little bit like how large the alpha, the number of samples over the dimension, can be, so that we are finding this way something close to zero test error, and we look at it as a function of the dimension to kind of have a good idea when actually whether this is something that persists as the dimension indeed goes to infinity. So when we do that, we get something like, going back to my axis, 2.5. So again, the stochasticity in the persistent stochastic gradient descent makes it that we need fewer samples to learn the phase retrieval to close to zero test error. And seems somewhat higher than what we needed. Here we don't really have this number kind of very precisely with the theorem, because studying the large time behavior of this scalar stochastic differential equation is still kind of complicated. So we did that only numerically. But we get something a little worse than the over-parametrization. But the message that the stochasticity in this case actually helps to reduce the sample complexity is again true. And this brings me kind of to the summary about the phase retrieval. So I introduced you this phase retrieval teacher-student setting that was a high-dimensional, real valued, because the phase retrieval will be complex valued. Usually here we had everything real valued, teacher-student setting, where the Gaussian input data and Gaussian teacher-generated weights. And I argued it's kind of a neat model to study learning with neural networks, because some of the things that we observe in much more complicated architectures and realistic data, etc., such as over-parametrization actually helping and stochasticity helping. Here, we see clearly that it manifests in this setting. So we saw that the sample complexity of the gradient-based algorithm can be improved with over-parametrization or with the persistent stochastic gradient descent. This is a solvable case of feature learning in high-dimensional over-parametrized setting. We don't have so many of those. There's a long line of work about over-parametrized neural network, but in the setting that is equivalent to kernel methods in a sense, where we are only learning the last layer, not really the features. Here we were truly learning the first layer. The persistent gradient descent is perhaps a curious variant of the stochastic gradient descent in terms of performance. We actually tried to run it on some like standard benchmarks and didn't see on standard benchmarks that it would improve the performance. But then we didn't see that for the stochastic gradient descent either. So there may be some more work to do in that direction. And that brings me that, despite like some results that we are happy about, there are still many things that we actually don't know how to do. I mean, there are some technical hurdles doing that. So for instance, the sample complexity of the gradient descent and how it depends on the loss and initialization and learning rate. If we don't, that's about controlling the large time behavior of this stochastic scalar process. It would be nice if we kind of got a closer hand on that. Another question could be, over-parametrization helped to get us to sample complexity 2. Can we get lower by maybe changing the architecture or maybe changing the algorithm even further? Can we get even closer to what the approximate message passing algorithm is able to do? Here we are in a system where we kind of have the advantage of knowing what is kind of tractably doable. Can we really close the gap? Or if we still don't know how to analyze the sample complexity of the gradient descent, if the number of hidden units actually was smaller than the dimension. The theorem that I showed you was we needed bigger than the dimension. So what if it is somewhere intermediate, the dimension half? Can we analyze how many samples are truly needed? Maybe more than 2, but how many? What would be the constant? We don't know how to do that. And the sample complexity of the stochastic gradient descent of the over-parametrized networks, kind of putting the two together, will they help each other, or will combining the two not help anymore? Empirically, actually, we tried and it didn't seem to improve much more over the two, but can we analyze that? So many things that one can kind of follow up working. So that's all from what I wanted to tell you. I don't know whether there are some questions in the meantime.
Okay, thanks, Lenka, for the great talk. So audiences, if you have any questions, please write them in the Q&A box. Before having questions, let me ask first a few questions. So basically, you have two problems. One is a standard regression problem, and the other is a phase retrieval problem. So I'm not quite sure about the kind of difference between these two problems. So for example, so you are taking the limit of n and d, and how this rate affects in two problems. Are they similar, or one is more difficult than the other?
Let me maybe go to that to that kind of summary slide. Where was it? Here. Right. So there are both a special case of this teacher-student setting. In the setting, the only thing that changes is that the teacher neural network in this spherical perceptron uses a sign function to generate labels. In the phase retrieval, uses an absolute value to generate labels. Okay. Otherwise, everything is the same. Now, in terms of the learning curve, like how many samples do you need to get a given performance, right? Mm-hmm. So the difference was kind of summarized here, right? You don't change much, you change sign for absolute value, as you're saying, what would it change, right? So what I see as a kind of key curiosity is that while nothing much changed, in the spherical perceptron, the ERM is basically base optimal. There is no gap between them. You run your logistic regression, that's it. You optimize the lambda, you're as good as you can get. If it was always the case, okay, you would go home. And now you just change the sign for the absolute value, and now things get different. You didn't do much, right? You just change sign for absolute value, and you get to a realm where actually the base optimal algorithm, or the kind of approximate message passing that goes after that estimator, is actually needing just 13% more samples than the dimension, whereas your vanilla gradient descent is just not working. Kernel's methods are needing way more samples than the dimension, and you actually need to go after variants of gradient descent, such as over-parametrize the network, and that helps the gradient descent, or stochasticity, and that helps the gradient descent to reduce the sample complexity. So it's kind of a setting where you have, you have two cases that are basically the same. You didn't change much, but it brings you from a problem where things are close to optimal, nothing particular for us to do to improve, and the other one where you can play games with what actually needs to be done with the architecture and the algorithm to get an optimal performance.
I see. I have one more short question. So in the analysis, N and D are both tend to infinity, but in practice, of course, they are finite. And you did numerical experiments, and in reality, so how big should N and D be?
So you see, for instance, in this figure, like the approximate message passing has dimension 10,000. The dimensionality of the system is 10,000, and you see that the points are on the curve as close as you can get. So that's kind of a curiosity of this. In essence, the proofs, right? They have some bounds and how fast actually the dimension needs to go to infinity for this to be true. And the theorems are in the limit, but then in practice, actually already this is 10,000. That's already pretty big. Like already, if you did a few hundred, it would actually lie on the line. So this prediction that this state evolution is actually giving you the performance of the algorithm that in math is in the limit is actually true already at decent sizes, say a few hundred. Of course,
is that tendency the same in the two problems?
Yes, that's the same in the two problems.
I see. Okay, thank you very much. So actually, we had already two questions in the Q&A box. Can you see them?
Let's see.
I think you may take a look at it and answer.
Thank you for a nice talk. Besides your rigorous proof, are there any intuitive explanations on why over-parametrized neural networks require less samples, alpha 2, than the non-over-parametrized method? Write most 3 methods in your performance of gradient descent slide. Can I call those three methods non-over-parametrized methods? So yes, I think yes, one can call those methods non-over-parametrized in the sense that they are really learning only one d-dimensional vector of weights, not more than that. Now, is there intuitive explanation of why is that? Well, not really, right? In the sense that in the literature, you have a lot of explanations that you can call intuitive. I don't know, like flat minima generalize better. And when you add parameters, of course, everything becomes much flatter. But fundamentally, none of them actually satisfies me, at least, because it does not really explain why the generalization properties are really kept. I mean, it's all those are kind of observations. So no, I don't have, I mean, you can go to some of those intuitive explanations in the literature and be happy with them. I'm not personally happy with any of them. To me here, kind of the fact that we can prove it is kind of remarkable. And I don't think you have many results in the literature that are actually doing that in the regime where one is learning the features. So not at this point that you think like much more intuitive. I will settle for proofs. Yeah, that's kind of what we did. Okay, thank you. So I go to the second question. Thank you for this interesting talk. Does persistent SGD perform better than GD and SGD do for the signal processing algorithm, such as matrix factorization and tensor decomposition? So, okay, that's a good question. I do not know. I do not know. We did not try, but it's a good question. Perhaps. I mean, it would be worth trying. Okay. Good suggestion. So I go to the next one. I hope that, okay. Thanks for the talk. I have two questions. Things keep moving, sorry. How about the case when the input data is not Gaussian, while other factors are the same? Okay, I'll start with this one. So that's something that I did not cover in this talk, but that, of course, I mean, you're rightly pointing that this seems like a huge limitation, right? No real data are Gaussian. How would that even be relevant? So this was indeed bothering us for a long time in this line of work, and in, say, past 2-3 years, we have a line of work about which I didn't talk today that actually relaxes that. So at this point, so we can completely relax that, actually have the input data to be correlated, and things depending only on correlation on the spectral density of the correlation matrix and another spectral density of a correlation matrix between the inputs and the labels. In the papers we have, this is kind of generic enough to, it seems like anything that is learning, that is, any neural network where you are fixing all the weights except the last layer can be described by that setting. So that kind of can be relaxed quite a bit. So for instance, any data that you can generate from a GAN is a data distribution for which we can kind of go through these calculations and have the learning curves. We are now kind of combining the analysis of the gradient descents with that, but on the level of the approximate message passing and these base optimal results, we actually do have the results for more general, more realistically looking data. And that's indeed kind of an important direction. I just didn't cover it today. And yours, the second part of that question, and how about the case when Y is a more common nonlinearity, such as ReLU and sigmoid of X times W, while other factors are the same? So that's something that we can do very easily. In the paper in which we prove the theorem for this free energy and the test error, we actually do have an example with a teacher using ReLU. Nothing, I mean, okay, what's kind of interesting is that information theoretically, the ReLU kind of needs, the student kind of needs exactly twice as many samples than it needs if it just was using a linear function, because the zeros are kind of not helping information theoretically without noise. So that's kind of not so counterintuitive. But if you look at the performance of the algorithm, the zeros are actually helping. So there is this kind of discrepancy whether you need twice as much also for the algorithm and you don't, you need a bit less. So that's kind of curious about it. And right, we could, I mean, if you have some concrete questions about the ReLU, this can, you know, whether I use a sign or a absolute value or any other kind of reasonably behaving nonlinearity such as ReLU, nothing much changes. Then what actually does change, nothing much changes for the part where I'm evaluating approximate message passing and the base optimal performance. What does change would be our result about over-parametrization. That paper and that proof was actually specific to the quadratic activation, and it doesn't go through if you replace that by a rule. So I could not claim that we did not manage to analyze or have analogous results for the over-parametrized neural networks with ReLUs rather than the quadratic nonlinearity. So that particular paper actually is specific to its nonlinearity. All the other ones that I was presenting are not, including the stochastic the persistent stochastic gradient descent. We could also analyze that with the ReLU. I would like to know how general the results are, because in practice, we cannot choose the data distribution to work on. Okay, so that I believe I answered. I mean, what we can do, I answered when I was answering about the limitation of the inputs being Gaussian. I can, if you write me a mail, I can send you the references about that. So that's indeed a limitation that we are kind of working through, and it's working pretty nicely. The limitation that is standing, and that in my point of view is crucial, is to actually go to multiple hidden layers. And or one can state it more kind of specifically, actually generalize our proof about the over-parametrized setting to a case where the width of the hidden layer is large, say ordered dimension, but the activation is not this quadratic activation. That actually is a technical hurdle that we didn't overcome yet. That is kind of the key limitation. Not so much the distribution of the data and not so much the details of, say, the algorithms. I hope that answers somehow the question.
Okay, thank you very much. So it's about time to conclude the seminar. So please join me to thank Lenka again for her great talk.
Thank you, Lenka.
Thank you, everyone, for listening.
So then, yeah, and this was the 14th round. So next round will be held in when is it? June 15th by Naonori Ueda from RIKEN AIP. He will be talking about machine learning technologies for disaster resilience. So it's more applied talk next time. Okay, so that's all for today. Thank you very much for joining us today. So have a good day in Switzerland and have a good evening in Japan. Bye-bye.
Thank you, everybody. Bye-bye.